This computer. Okay, so let's start with chapter. Looks like I had an unstable internet connection. Hopefully, not too bad. Okay, well, this particular chapter deals with a topic which is called. Oh, we got one more. A topic called stoichiometry. Okay, and basically it's related, very much related to the balance of the chemical equations that we were doing in previous chapters. Okay, so for example, if we look at this reaction where we have nitrogen monoxide reacting with oxygen to give us nitrogen dioxide, once we balance it, we get the coefficient. So there's 2 in front of nitrogen monoxide. There's understood to have a 1 in front of oxygen, and there's a 2 in front of nitrogen dioxide. So I was using examples where I talked about 2 molecules, for example. 2 molecules of NO need 1 molecule of oxygen gas to give us 2 molecules of nitrogen dioxide. And if I were to up that number of molecules and say 10 molecules of nitrogen monoxide, well, based on the ratio, the mole ratio of the balanced chemical equation, that means that I need at the minimum 5 molecules of oxygen, which then would give me 10 molecules of nitrogen dioxide. So, but we work in terms of moles. So we're going to change that molecule name to moles. Remember that moles is equal to 6.02 times 10 to the 23rd molecules. In this case, they're molecules of each reactant and products. Because the mole concept is simply a number, okay? Just simply a number. And it just happens to be a very large number. So now, we can remove the molecule terminology and stick in the moles. So what we're saying here is 2 moles of nitrogen monoxide require 1 mole of oxygen, which then will gives us 2 moles of nitrogen dioxide. Okay. Similar with respect to this other reaction, where we have nitrogen in the presence of hydrogen gas to give us NH3, otherwise known as ammonia. Once we balance it, okay, we end up with 1 molecule of nitrogen, 3 molecules of hydrogen gas, and which gives us 2 molecules of product, in this case, ammonia. Taking out the word molecule, we can say that 1 mole of nitrogen is required for 3 moles of hydrogen gas, which gives us 2 moles of ammonia. Now, those ratios, those coefficients are very important. So we have to make sure we balance them correctly when we balance the chemical reaction, because we're going to utilize those, that mole ratio with respect to doing calculations involving chemical reactions. Okay, so those numbers are what we call mole ratios. Let's take, for example, the following reaction where we have 1 mole of iron 3 oxide reacts with 3 moles of carbon monoxide. See that CO carbon monoxide, which, excuse me, gives us 2 moles of iron, the element of iron, and 3 moles of carbon dioxide. So if we look at the coefficients in the front of the balanced chemical equation, we have these mole ratios that we can utilize. For example, we have that relationship here where we have 1 mole of iron 3 oxide over 3 moles of carbon monoxide. Now we can write it in that form, or we can invert that ratio and write it in this form where we got carbon monoxide in the numerator. Okay. Now, the other relationship we can look at is the relationship between the iron and the carbon monoxide. And that relationship is just one ratio written here, is 2 moles of iron per 3 moles of carbon monoxide. That same ratio can be inverted and written in the other direction, okay? And with carbon monoxide on top. And so what we have here are mole ratios that we can utilize to do the calculations. Now, recall back when we were doing conversion of the units, okay? I did mention that every ratio, every conversion factor was a ratio that we can write in one or two manners. Whatever we're looking for will be in the numerator. So if we do a calculation and we're trying to calculate how much iron 3 oxide we need, then we would utilize this ratio right here because we have iron 3 oxide in the numerator. And we set up our conversion factors so that we can follow the units and making sure that the units cancel out when we do the mathematics, okay? Now we have here, let me point this out. We have the relationship between, oh, that's way too big, iron 3 oxide and carbon monoxide, okay? And so that's one set of ratios. That's 2 ratios right there, okay? Now, we also have a relationship between the iron 3 oxide and the iron. Again, 2 more ratios set up there with either iron in the numerator or iron in the denominator. We also have a relationship between the iron 3 oxide and all the way over to carbon dioxide. And that's a 1:3 ratio or mole ratio. Again, we can set up 2 mole ratios for that relationship. Now, we can't forget the other relationship between carbon monoxide and iron. That has its own relationship of 3:2. And carbon monoxide and carbon dioxide, which in this case is simply a 1:1 because it's a 3:3. And so we have so far 2, 4, 6, 8, 10 ratios that relate the reactants with each other or the reactants with the products. And then we have one last one, which is the relationship between the iron and the carbon dioxide, the 2 products, which is a 2:3. And so in essence, we have a total of 12 ratios that we can utilize for any calculation that we need to do, okay? And and the other aspect about why this is so important is, for example, we could get a problem that we're dealing with iron 3 oxide and talk about grams. Well, if I start off with 10 grams of iron 3 oxide, how many grams of carbon dioxide do I get? Well, I cannot go directly from grams to grams when I go from A to B. I have to go through a common factor, and that common factor is moles. So once I convert iron 3 oxide to moles, then I can go to moles of carbon dioxide, which from there, given the molar mass of carbon dioxide, I can then go to grams of carbon dioxide. Okay, and we'll have a flow chart to demonstrate that. All right, and so let's look at the first problem here. They're asking you here how many moles of iron can be formed from 10.2 moles of carbon monoxide. All right, so the point being here is we're dealing simply with iron and carbon monoxide. That's it. What's happening with carbon dioxide or what's happening with iron 3 oxide, it's not important because the question here is simply asking us how many moles of iron can be formed from 10.2 moles of carbon monoxide. The assumption is that you have enough of the other reactant to give you this reaction, okay? And so once we know now that we're going to use the ratio of 2 iron per 3 carbon monoxide. Now, how do I know that I want the iron on top? Because that is what I'm looking for. I am looking for moles of iron. So that ratio that I utilize would have moles of iron in the numerator, okay? And so I take 10.2 moles of carbon monoxide, keep track of my units, Note here that moles of carbon monoxide cancel out, which tells me that I set it up properly with respect to the units, because the only units I got left now are moles of iron. So I simply get 10.2 multiplied by 2 divided by 3. Therefore, my answer is 6.80 moles of iron. So 6.8 moles of iron are formed or produced if I start off with 10.2 moles of carbon monoxide. Okay. Now, right now we're dealing with just moles, but the next step is, because we can look up the molar mass of iron in any of these compounds, and the molar mass is given in units of grams per mole, note another ratio. So once we're at moles, we can very simply go to grams, because in the lab is what we measure, grams. We don't measure moles on the balance, we use grams, but we take those gram units and convert them to moles based on the molar mass, or the molar mass of the reactants or product. Okay, now let's take a look at the next one. The next one says, how many moles of iron 3 oxide, and let me clear it up a little bit so we know what. Okay, they're asking you how many moles of iron 3 oxide are needed to form 17 moles of carbon dioxide. So we are dealing with iron 3 oxide, okay, and we are dealing with carbon dioxide. And so the way it's saying here, I would need to make 17 moles of carbon dioxide, all right? 17 moles, I need to make 17 moles of carbon dioxide. The question is, okay, well, that being the case, how many moles of iron 3 oxide do I need to make 17 moles of carbon dioxide? And so again, we can use the mole ratio of 3 carbon dioxides per 1 iron 3 oxide, okay? So we set this up and we write down what we're given, 17 moles of carbon dioxide. Our mole ratio is a 1 to 3 with iron oxide in the numerator, okay? Double check your units. You can see that carbon dioxides cancel out, leaving you with units of moles of iron 3 oxide. So then you take the 17, you do the math now, divided by 3, you end up with 5.7 moles of iron 3 oxide. And so in order to make 17 moles of carbon dioxide, I need to start off with 5.7 moles of iron 3 oxide, is what we just calculated. And we utilize this. I mean, this is the reaction that occurs that we can do in the lab in small scale, or if we have an industrial plant, if for some reason this is how we want to make carbon dioxide and iron, by taking iron 3 oxide and treating it with carbon monoxide, we can do this in industrial size, big old industrial plant. The ratio is still the same. Okay, the chemical reaction is still the same, the ratio. So we could have said easily, instead of 17 moles of carbon dioxide, well, how much iron 2 oxide do I need if I need to make 17 million moles of carbon dioxide? Same ratio, same setup. All right. Excuse me. And so the mole ratios are very crucial. So that's why it's important that we balance the chemical reactions properly, because those coefficients give us the mole ratios, and having those mole ratios then allows us to do calculations. For example, we have this reaction where we have sulfur dioxide in the presence of oxygen gives us sulfur trioxide, okay? And so we can put a 2 in front of sulfur dioxide and a 2 in front of sulfur trioxide, and everybody's balanced. So we got 6 oxygens on the reactant side. We have 6 oxygens in the product side. We have 2 sulfurs in the reactant side, 2 sulfurs in the product side, okay? remember, in front of the oxygen, it's understood that there's a 1 there. And so what this balanced chemical reaction tells us, we have 2 moles of sulfur dioxide require 1 mole of oxygen to give us 2 moles of sulfur trioxide. Okay? So first question is, how many moles of sulfur trioxide will form if 0.1665 moles of oxygen react? Okay? And so we're looking at the relationship simply of sulfur trioxide and oxygen. That's it. Don't care about sulfur dioxide, just what I just highlighted there based on the question being asked. Okay? It's assumed that you have a sufficient amount of SO2, sulfur dioxide, for this reaction to proceed with the problem that you're given. Okay? And so we, just like the previous examples, we write down 0.165 moles of oxygen is what we are given. Okay? We use the mole ratio of 2 to 1, sulfur trioxide to 1 oxygen. And so notice that our units again cancel out. Okay? Now, right now we're setting up 1 conversion factor. But as we progress with the chapter, in the next chapter, we're going to find we're going to have at least 3 conversion factors to go from point A to point B. Okay? And I know some are still wanting to do the single ratio method of doing these type of calculations. You know, when we get to 3 ratios, that thing might get a little bit mixed up a little bit. So, but if you set them up with this method and you follow through with your units, you should not have a problem. Okay. All right. The next question, and let's clear it up so we can see what we're doing, is how many moles of sulfur dioxide are needed to make 0.42 moles of sulfur trioxide. And so we're dealing with sulfur trioxide, and we want to know how many moles of sulfur dioxide I need. And so think about this. They're asking you, okay, I'm starting out, I want to make 0.042 moles of sulfur trioxide. I want to make that much product. How many moles of sulfur dioxide do I need? Okay. And sometimes in the beginning, when you're working through these type of problems, it helps to mark and identify what I just did with the boxes, right? So I know who I'm talking about, which 2 reactants and which reactant, which product I'm interacting with. And then it helps for me to write down what the question asks, what I'm given and what I'm trying to find. Okay. Once I do that, I can set up my problem. And so I write down what I'm given, which is 0.42 moles of sulfur trioxide. Then comes my conversion factor, which is a 1-to-1 mole ratio, because it's 2 moles of sulfur dioxide per 2 moles of sulfur trioxide. Okay. Do a quick check. Make sure that my units are canceling out properly. And they do. The sulfur trioxides cancel out, leaving me unit-wise with sulfur dioxide. So that tells me I set this up properly. And 2 over 2 is simply 1. And so 0.042 moles of sulfur trioxide require 0.042 moles of sulfur dioxide. Okay. Simply because it's a 1-to-1 relationship here. Quite different from the previous example where the relationship is a 2-to-1. So I need to double the amount, okay, because of the mole ratio difference. Okay. All right, so this flow chart kind of puts it together, and we're going to have another flow chart here in a bit, kind of encompasses a little more information, but you can see here that if you're given grams, in the problem, and I need to find grams of another material. Okay, this is the route I'm going to have to go through. Now, this is going from left to right, but keep in mind, I can go from right to left. Okay, those arrows should be really a double-sided arrow. I can go in both directions here. In fact, it should be written like this. Okay. All right. And so notice what I'm starting with, this could be, I'm just going to arbitrarily say compound A. Okay. And this is compound B, whatever B may be. All right. All right. I've got to go from A to B. But in order to get to that point, I can't go directly grams to grams. I have to go through moles. Okay. Moles is the common factor that these types of chemical reactions use. So moles, right there, where I'm highlighting. Okay. To get from point A to point B, I got to go through moles. So I need to take my grams and convert it to moles. Well, in order to do that, I need the molar mass. Okay. And sometimes the problem is written out. So this is where we get into writing formulas. This is where we do. Remember, we started off with the periodic table. From the periodic table, we started talking about the ions, and we put the ions together to make compounds. And now we're putting compounds together to have chemical reactions, okay? And so we need to be able to write the formula correctly so that we can calculate the molar mass. And the molar mass simply is the sum of all the atoms in that compound. And we look up the atomic weight for every atom on the periodic table that we supply, which brings me to a point. When you have to use the atomic weights or the molar mass of the elements, okay, use the atomic weights on the periodic table we supply. I realize you can go on the internet and you can get a variety of different atomic numbers, and that's fine. However, Canvas, the answers in Canvas are based on the atomic weights that we give you on the periodic table. So if you use another atomic weight, which could be different a little bit as far as the 100th place, it could change your answer. And then when you put that answer in the Canvas, it doesn't understand it. Okay, now I will give you credit because that 100th place is not that much of a difference. But to prevent that from happening, use the atomic weights from the periodic table that we supply. All right, so from the molar mass, and we're given grams, we divide by the molar mass. The molar mass, remember, has units of grams per mole. And if I want moles, I revert the molar mass. So I have moles per gram to give me moles given. Okay, the mole ratio right here comes from the balanced chemical equation that from the examples we were doing just now. Okay, so you can see that I start off with grams of A, and when I use the mole ratio, now I am moles of B. So now I moved into B. And from the molar mass of B, again, molar mass is grams per mole. I simply multiply from the moles of B to give me grams. So that's how I can get from A to B in as far as grams are concerned. The examples we were doing right now, we weren't in grams. We were simply moles given, looking for moles find. Okay, so just expanded it now because remember when we actually do this in the lab, we're actually weighing out samples. We're weighing out in grams, and we convert that to moles. All right. So if we look at this reaction, here we have 3 iron, 2 oxides reacting with 2 aluminums to give us 3 irons and 1 aluminum oxide. Okay. Oh, what type of reaction is this? Anybody know by chance?
Sorry, can you say that again? My phone was glitching out.
Oh, okay. What type of reaction would this one be? Kind of a side. We got iron 2 oxide reacting with aluminum.
Single replacement?
Yeah, single replacement. Very good. Yes, it is. Okay. Single replacement, you got it right too. Rebecca. All right. So we got a single replacement reaction. Then we look at the ratios. We got a 3:2 with respect to iron 2 oxide and aluminum and so forth. All right. So the first question is asking you, calculate the mass of iron 2 oxide needed to react completely with 5.5 grams of aluminum. All right, so let me clear this up a little bit. And so for the first part of this, there's a two-part question. The first part, they're asking you simply about the iron 2 oxide and aluminum. That's it. Okay. If I start off with 5.25 grams of aluminum, how many grams of let me write that in. Like I said, I write them down so I can follow. If I start with 5.5 grams of aluminum, how many grams of iron 2 oxide is needed, is what the question is asking. Okay. Then the second part says, change this a little bit. Calculate the mass of aluminum oxide produced when 10.25 grams of aluminum completely or reacts completely. So for this part, our only concern is the iron aluminum oxide, which, by the way, is something you find on sanding paper. It's very coarse material, and aluminum. Okay, so the two yellows are for the second part of the reaction, and they're saying if I start off with 10.25 grams of aluminum for the yellow part, how many grams of aluminum oxide are produced? Okay. And so now I know just by marking the equation and knowing which reactants and products I'm working with and now what I'm given, I can start setting up my my solution. Okay. Okay, so the first part, you start off with 5.5 grams of aluminum. The reaction is still the same. Now, I need to get to moles. Okay, for any reaction, when I start in grams, I got to get to moles. So I need the molar mass of aluminum. So I go to the atomic periodic table, find the atomic weight for aluminum, and it is 26.98 grams per mole. And so since I'm looking for moles of aluminum, I write it with moles in the numerator, grams in the denominator. Okay. Then this comes from the mole ratio of the reaction because I'm I'm working with the two reactants, the iron 3 oxide and the aluminum. So at this point, and this is where you check yourself as you go along, as I am setting up my problem, notice that my grams of aluminum cancel out unit-wise. My moles of aluminum cancel out. And I went from moles of grams of aluminum. So at this point, if I were to do the mathematics up to this point, I'm now converted to moles of aluminum 2 oxide. You see? So you see how this is how I went from apples to oranges. Started with apples, and now I'm at the orange. Two unrelated things, but the relationship they have in that example, in that analogy, is fruit. Here, the relationship between reactants is moles. Okay, I got to get everything to moles. So now at this point, I'm at moles of iron 2 oxide, which now I need one more conversion factor to get me to grams, because we're trying to calculate how many grams of iron 2 oxide I need if I start off with 5.5 grams of aluminum. And so now I need the molar mass of iron 2 oxide. Okay. And again, I'm keeping track of my units. Unit-wise, I am now, unit-wise, at grams of iron 2 oxide, which is where I wanted to be. So you might notice something here. When I start off with grams and I want to get to moles, I divide by the molar mass, which now gets me into, now once I'm in moles and I want to get to grams, guess what? I multiply by the molar mass, okay? So if I'm in grams, I want to get to moles, I divide by the molar mass. If I'm in moles and I want to get to grams, I multiply by the molar mass. And you can see that by my units if they're set up properly. So that ends up as 22.2 grams of iron 3 oxide. What does that mean? That means if you started off with 5.55 grams of aluminum, I need at the minimum, bare minimum, 22.2 grams of iron 2 oxide for this reaction to proceed as written, okay? All right, so you can see how I went from totally dissimilar species, but in doing so, I had to go through moles, okay, and the mole ratio. All right, the second part was, all right, I have 10.25 grams of aluminum. We were trying to figure out how much aluminum oxide we're going to make if I start off with 10.25 grams of aluminum. So again, like the first part, I need to convert that aluminum to moles. It's a given. You got to go to moles, okay? Then the second part is the mole ratio that equates the aluminum to aluminum oxide, okay? And so that comes from the balanced chemical equation. 1 aluminum oxide to 2 aluminum. So again, as I'm setting these conversion factors, keep track of your units. My grams of aluminum cancel out. My moles of aluminum cancel out. Okay, so at this point in time, I'm in units of moles of aluminum oxide. Well, the question asks to give you your answer in grams, so I got to take it one more step. I need the molar mass of aluminum oxide, so I look up the atomic weight for aluminum. There's 2 of them. Look up the atomic weight for oxygen. There's 3 of them, okay? So I got 3 oxygens, 2 aluminums, add up their individual, all the atomic weights, and I end up with a molar mass of 101.96 grams of aluminum oxide per mole of aluminum oxide, okay? So again, once I put in the molar mass, check my units one more time. It's always a good idea to do that as you progress. And then now, unit-wise, you are where you need to be based on the question asked, and that's in grams of aluminum oxide. Now the mathematics is up to you. You plug in the numbers in your calculator, double check yourself, and you should end up with a value that is 19.37 grams of aluminum oxide. And so what does that mean? That means if I start off with 10.25 grams of aluminum, run the reaction, I'm going to end up, after the reaction's done, I'm going to end up with 19.37 grams of aluminum oxide. And the assumption is that these reactions are 100%. In the real world, no reactions are 100%. But this is the theoretical amount that one should calculate to receive if, in fact, you start off with 10.25 grams of aluminum. Okay. The same is true for the example number 1, that 22.2 grams is the calculated theoretical amount needed for this reaction. Right. So let me clear this up a little bit. All right. So this particular flow chart, very important because it puts everything together for you. Okay. And if you grasp this flow chart, and then you shouldn't have a problem. All right, the very top, we're going from top left corner to top right corner, okay? We cannot go directly, and just like the example we just did, we have to go through moles. Hey, excuse me. In the previous examples that we were doing, excuse me, I'm having a little bit of a talk thing. When we were doing the examples, we were given moles given, okay? We were in the white boxes, okay? In the beginning of this chapter, we were in the white boxes. We were just given the moles, and we utilized the mole ratio to get from point A to point B. But this expands it because you know the molar mass, okay? The molar mass is in units of grams per mole. And the other relationship, and that was only at STP, and only if it's a gas, you know that for 1 mole of any gas at STP, it has a volume of 22.4 liters, okay? Then the other aspect is the mole ratio. That comes from the balanced chemical equation. So you got to be able to balance that chemical equation to get the right mole ratio. And so we can go from the top left corner to the bottom right corner only if we are at STP, only if we have the correct mole ratio, okay, and only if we know the molar mass to get us from the top left corner to the bottom right corner. That's going from left to right, but bear in mind, you can start at the bottom right corner and go to the top left corner. Okay, you're not limited to that. All these arrows really are two-way arrows. Two-way arrows. You can go in multiple directions. In fact, let me make these arrows two ways. Okay. So you're not limited, like I stated, going from one way to the other, because you can start at the bottom corners in the yellow region and go up any direction from that point. Okay. So that part is important as far as grasping this particular calculations, all these calculations. This flow chart here answers the questions. We just did the examples in the green where we were grams given and we're working our way to grams find. Okay. Now you can add the STP conditions. All right. For example, this is write and balance the reaction of hydrochloric acid in solid cobalt. Okay. And so they're telling you, here's the reaction presented to you in words, and you got to take those words and convert it into a chemical reaction. all right? And so they're also telling you that cobalt is in the +2 state, oxidation state. Cobalt is not of the 16. Remember, the 16 have a constant oxidation state. Cobalt, all the other ones varied depending on the conditions. So they're having to tell you here, cobalt is in the +2 direction, oxidation state. And so the reaction is hydrochloric acid plus cobalt gives us cobalt 2 chloride plus hydrogen gas. Okay. Now, how do we know that reaction proceeds? Well, here we go. Oh, where'd I go? Where'd it go? Okay. If we look at the activity series on the periodic table, we will find that cobalt, so we got hydrochloric acid. You remember the activity series is just underneath, right above the solubility rules. Let me see if I have it written here. Yeah, let me pull it up because it's important that I show you this. Where it go? Come over here, chemistry. Okay. Okay, on the periodic table, and I'm sharing the activity series. All the activities here are relative to hydrogen. Okay, hydrogen. Now, hydrogen, elemental hydrogen, as you well know, is diatomic. It's H2. Remember when we were, at least when we talked about these type of reactions, single replacement reactions, we look up to see which metal was more reactive. And then the next question was, okay, is the most reactive metal in ionic form already? Is it in a compound form? If it's not, then reaction proceeded. If it is, then there's no reaction. Well, here, when we're dealing with hydrochloric acid, we're dealing with the, that's the ionic form of hydrogen, H2. H plus, it could be either H plus or in water, okay, as far as the ionic form of hydrogen. And so if we go back to the problem, and we compare the reactivity of hydrogen and cobalt, we see that cobalt is the most reactive of the two. And then the second question is cobalt in an ionic form? The answer is no. Okay, so therefore this reaction proceeds, and more specifically, cobalt goes to the +2 state. So you write cobalt and then Cl2, and then hydrogen, which is now converted from the ionic form of H plus to the molecular form of hydrogen gas. Okay, so if the reaction, instead of cobalt, let me go back for a second. We were reacting that with copper, let's say HCl and copper, guess what? It wouldn't react because hydrogen is more reactive than copper, and hydrogen is already in ionic form, which is H plus. And the same would be true for silver, mercury, and gold. Okay? H plus, there would be no reaction. All right, let's go back to that. And so after that, we balance it out, and we end up with 2 HCl aqueous, cobalt solid, and this is basically a single replacement reaction. Okay, cobalt 2 chloride and hydrogen gas. All right. Now, question here says, how many liters of gas at STP will form if 5 grams of cobalt reacts? All right. And so our only concern is we're asking about cobalt and hydrogen, okay? And if we start off with 5 grams of cobalt, they're asking you, all right, well, how many liters of hydrogen are created is the question, okay? We look at the relationship there. It's a 1-to-1 as far as the mole ratio, okay? I did check, I forgot to check, is that balanced chemical equation? And it is. It's a balanced chemical equation, so that ratio is correct. It's a 1-to-1. Second of all, we are at STP, therefore we can utilize the 22.4 liter per mole relationship, which again is another ratio. All right, so let's write down what we're given. We're given 5.0 grams of cobalt. Conversion number 1 has to be moles. I need to convert cobalt into moles. So I look up, excuse me, the atomic weight of cobalt, which is 58.93 grams per mole. I write it with moles in the numerator. Why? Because I want moles of cobalt, okay? My grams of cobalt cancel out. All right, now, from the balanced chemical equation, I know there's it's a 1-to-1 relationship, 1 hydrogen per 1 cobalt, okay? So at this point, I now have gone from grams of cobalt, now I'm in moles of hydrogen, okay? And being at STP, I can very simply now insert the final factor, which is 22.4 liters per mole, because that now tells me, since I know how many moles of hydrogen and I know I'm at STP, I can calculate how many liters of hydrogen gas are created. And I end up with 1.90 liters of hydrogen, okay? And so if you think about it, if you go back to the table, we are going from, let me clear this up here. We have gone essentially from grams given all the way to the far right corner in that flow chart. And so grams given, we needed the molar mass to give us moles given. We needed the mole ratio to get us into moles. And since we were at STP, we can simply use the 22.4 liter per mole relationship to give us the volume of gas, okay? Now, we could have, depending on the question, we could have gone in that direction and give it that answer in grams, okay? But that is an example of that flow chart. Okay. We could have very readily started from the grams of hydrogen and work backwards to calculate how many grams of the starting material we need. Okay, and so that's an example of using that flow chart. Now, here's the other example where if 2.374 liters of hydrogen gas form, just like I showed you on that flow chart, how many grams of hydrochloric acid reacted, okay? And so now our relationship is simply between hydrogen gas and HCl, right? And if we have 2.374 liters of hydrogen gas, the question's asking how many grams of hydrochloric acid I need. Okay, that's what they're asking you there. Okay, and so I go to the flow chart to help me out and refer to it until you're comfortable with this. Plus I'm at STP. So being at STP, I can utilize, I'm starting at the bottom right corner of the flow chart. Okay, let me go back to it. I'm starting at the bottom right corner of the flow chart, and I need to go up to find grams fine. I'm moving up to the bottom top right. Okay, excuse me, top left, which is grams given. Okay, that is what I'm looking for. Okay, so we write down what we're given, 2.374 liters of hydrogen gas. Okay, I am at STP, so I can use that relationship of 22.4 liters per mole. That gets me into moles of hydrogen. Okay, once I'm at moles of hydrogen, remember, whether I start with liters or I start with grams, I gotta get to moles. That's my first step. And if I start with grams, then like the previous example, I need the molar mass. If I start with liters, then I'm at STP, then I can use that relationship. If I'm not at STP, I'm at liters, I can't do anything at this point. Okay, I'm stuck there. I can't move. Not enough information given. Then from the balanced chemical equation, I know that there's 2 moles of hydrochloric acid per mole of hydrogen. Okay, and from that point, now I need the molar mass of hydrochloric acid, which is 1 chloride, 35.45, 1 hydrogen, 1.01, total atomic mass or molar mass of 36.46 grams per mole. Okay, so at this point, and as you go along, check your units, making sure that your units are canceling out correctly. Okay, and so at this point right there, unit wise, before I even do any mathematics, my units show me that I am grams of hydrochloric acid. Okay, now you can plug in the numbers in the calculator. And you should end up with 7.72 grams of hydrochloric acid. Okay, if you want to make 2.374 liters of hydrogen gas at STP, you must start off with 7.72 grams of hydrochloric acid. That is what that calculation is telling you. All right. So here's another word problem. They're telling you in words, hydrochloric gas plus oxygen gas produce chlorine gas and water vapor. Okay. And so here's something interesting. All these reactions are in the gas phase. So hydrochloric HCl(G), as far as the physical state, hydrogen gas, oxygen gas. Remember, oxygen is diatomic, so it's O2. And chlorine gas is also diatomic, have no fear of ice cold beverage. Okay, so it's Cl2. A big mistake is not remembering, if they did not put the term gas after chlorine or oxygen, then yes, you're dealing with the single atom, but that's highly unlikely. Okay, if you're dealing with all the diatomics, have no fear of ice cold beer, you are dealing with 2 of them. Okay, and then water vapor, H2O. So hydrochloric acid plus oxygen produce chlorine and water vapor. Okay, so there's the reaction, and it's balanced. So it requires 4 HCl. 4 moles of hydrochloric acid require 1 mole of oxygen to give us 2 moles of chlorine gas plus 2 moles of water. All of them in the gas phase. And the question is asking you, how many liters of chlorine can be formed if 3 liters of oxygen react completely at STP? Okay, so how many dealing, excuse me, with chlorine and oxygen. Okay. And the other thing I noticed that I am an all in gas phase. So this could be an important factor that I can utilize here in a second. But let's write down what we're given. We got 3.00 liters of oxygen gas. Okay. First step in anything, we got to convert to moles. So we are at STP. We're dealing with the liters, so we can use that relationship. Okay. So that gets us into moles of oxygen gas. Then we look at the mole ratio, which is 2 moles of chlorine per 1 mole of oxygen. So that gets us into moles of chlorine. So we were at moles of oxygen. Now at this point in time, we are in moles of chlorine. And the question is asking how many liters. So we can, again, because we're in STP, utilize that factor to put us back into units of liters. And then do the math, we end up with 6 liters of chlorine gas. Now notice something interesting is that the 22.4 liters per mole, don't they each cancel each other out? They sure do. Okay. And so I can simplify this calculation by simply using the mole ratio of the balanced chemical equation. And this is only true, I emphasize this, is only true when all of the reactants are gas and we are at STP. Okay. We did an example earlier where one was a solid and we had to convert that solid grams into moles and then go to gas. Okay. And so we needed the molar mass there to do that. Here, if everybody's in gas, if the 2 reactants are in gas, and those are the ones we're going to calculate, we can just simply use the stoichiometric ratio between the 2 that we're calculating and not worry about the 22.4 liters per mole. Okay. Any questions about that? But when, until you're comfortable with it, do by all means put in 22.4 liters per mole until you're comfortable with that and how you recognize that you can cancel it out. And by all means, continue to use it. All right. You might want to try these at home. The question is given to you. Carbon reacts with oxygen to form carbon monoxide. And then the question is, how many liters of carbon monoxide at STP can be made if you start off with 10 grams of carbon? Okay. And the second part, how many liters of carbon monoxide can be created if you start off with 20 liters of oxygen? Okay. And you should end up with 28 liters for the first example and 40 liters for the second. All right. Now, basically, these calculations, okay, we started with the elements, as I mentioned. From there, we went to making compounds, be it ionic or be it covalent. Okay, so from the elements, we went on with ionic compounds, covalent compounds. Then we utilized the compounds to actually start reactions with each other, with reactants. And we learned about how to balance some of these reactions. And from the balanced chemical reactions, we determined or recognize the stoichiometric ratio between the reactants and the products and, all the different combinations. But the coefficients gave us those ratios, okay? Once we know that, okay, we can make calculations of reactants and or products based on these ratios, and we can make these calculations in terms of moles, in terms of grams, or in terms of liters if we are at STP. Okay, I emphasize that, only at STP. And this particular flow chart is important. You grasp this flow chart right here. You should not have any problems, hopefully, with going from point A to point B. And the thing to remember, you always have to go through grams. I've seen examples of students doing calculations. I don't know how they did it, but they're incorrect, where you took grams of A and created grams of B without going through moles, okay? That's not possible, right? Um, highly impossible given the information you're given. Let me restate that in that manner. So refresh your memory on molar mass and how you can go from grams given to give me moles to moles given, okay? Refresh your balancing the chemical reactions because you need that mole ratio here to get you from A to B, okay? And then obviously, if you're at STP, you got 17.4 liters per mole. So anyway, this flow chart here kind of puts it all together for you. Okay. That being said, that is the end of chapter 13. Congratulations. We got 2 more chapters to do. Okay. In fact, we're a little bit ahead. And what I want to do is actually not continue with chapter 14. Given today, you have, don't forget, you have exam number 4 today, and that's chapters 10 through 12. So I would like to stop it here, and then next Friday, you come back, I'll continue with chapter 14. That's a little bit longer chapter. Chapter 15 is fairly short, about as short as this one. But 14 takes a little bit longer, maybe a couple of sessions. But after that, we get knocked out with chapter 15. I'd like to be able to give you some study days. Now, on the 20th, I won't be here. It's next Friday. I have an appointment that I must attend. So I won't be here for any Zoom lectures. But obviously, you have any questions, send them to me email. Okay. All right. We have any questions? Let me